Hi, my name is Vahan Davoudian. I'm a physics experimentalist for 30 years. Sorry, I cannot be in the picture because these are so small. I have to zoom it. First of all, I'd like to thank YouTube for this wonderful opportunity for us so we can upload our videos, our experiment and everything else so people can watch and they can do theirs and then we can watch and we can learn. And in fact, I'm thinking they are like a huge university. Everyone can benefit from YouTube and they do a fantastic job. We appreciate that and I don't know how to thank them, but overall everything is working real fine. And then I uploaded so many theories, people called me, they love it. And how could I do that without YouTube? As a matter of fact, I call them synapse. Synapse is in the human brain, is like a junction which is connecting billions of neurons. That's exactly what YouTube does. YouTube is connecting everyone. It doesn't matter where you are, how your ideas are, or what is your expertise. It doesn't matter. You can connect with everyone. And we appreciate that. And today, in fact, my main thing is about Michael Faraday, one of the greatest experimentalists of all the time. I mean, he was amazing and then he was so genius. And in fact, today my theory is called Induction motors can operate mechanically with DC by Vahan Davoudian, physics experimentalist, email vahandavoudian@aol.com. In fact, it was so difficult for them at that time. I'm talking about 200 years ago, and I remember on July 20th I had my general theory for 4 parts, and then I took you guys back 500 years when Copernicus was there, and today I take you back 200 years, 1831. But unfortunately, you know what, when I was a little kid, I was doing electric motors and then I knew Michael Faraday, but I could not even read at that time. But then I realized he was genius. And imagine, one day in 1977 in Los Angeles, I had a friend, he was getting his PhD in physics. And he was in Caltech. He said, "Juan, I have a surprise for you." So he took me to an old place. And then he said, "There's a book, special book, very old, but we cannot buy or do anything. All we can do is take notes. We cannot even take it home anyway." So we took some notes. And then I realized there's so many things missing. And then now, I had to go back almost 200 years and then exactly replicate what happened when Michael Faraday started his coil. And unfortunately, all in the books we can see is something like this. It's like a coil like this. Well, of course, these are new. These are around like from 1960s, maybe you can see. But you know, Michael Faraday's time was so different. He had a problem because it was bare wire. And then I saw in that book in LA that, you know, he had to get a thread like this, and then go one by one. It would take forever. Well, of course, this is a little bit thick, and this is so thick, it's just exaggeration, so you guys can see it. But he had to do this almost days and days, but nowadays it's just so easy. We get this. It's already taken care of. All we have to do is just wind them, and they won't short it anyway. And then I said, I better replicate exactly the way Michael Faraday did. It was so boring, so strenuous, and it was killer. It took me almost 2 days to replicate his thing like this. Well, of course, this is not as good as the way he did because he used fine wires. God knows how many months and days, you know, he worked on it. Anyway, I did this. I show you, this is amazing magnet. Even though it's not powerful like this, guys, if I do like this, but you know it works. Let me turn it on. You can see how powerful this is. I measured this. This is the 1,000 Gauss. Let me turn it on. Did you see that? I have this Gauss meter which is helping me a lot. Let me show you. This is a DC gas meter, and it's, precision is almost 100%. And it goes to 20,000 gas, which is more than enough for me. I show you, when I turn this on, this is never going to be as good as, the other, this is not going to be good because it's not a lot of, coil on this. But, let me turn this on, you can see, this must be at least 1,000 gas. See, it's showing 1,200. See, 1,100 gas, which is more than enough. Well, of course, today we will work about the neodymium. This is the most expensive and most powerful one. I removed this from the computer hard drive. And guess what? This little magnet has almost like 4,000 gas. And that is so good. This is the most powerful magnet in the world. There is no way you can demagnetize this. Coercivity of this is so high, it's just almost impossible. But a magnet like this is ceramic. We can demagnetize this. But this one we cannot. I show you. This must be at least like 4,000 gas. Let me show you. See, 3,590 gas, which is more than enough. Anyway, so he did this, and then he realized that, he had to do this famous experiment. Let me show you. We changed the history. So what he had to do, he had a coil like this, and like I said, that coil is so easy now because we have these thin wires. His was so bad, but the concept was the same thing. So he had a core, a little bit core here, ferromagnetic probably, and I have no idea how big the coil was, but the concept 200 years has not been changed. So either I move this coil against the magnet or the other one gets this. It doesn't matter. As long as I have a motion, so you can see we get induction. So I connect this now, you can see. Just bring it a little bit closer, you can see. You see? I'm getting almost 3 volt AC, which is not bad. Well, of course, the faster you move, the more induction you get. And this was a genius idea because whole our life depends on induction. And Michael Faraday, what he did, he just changed the world. And in fact, in that book I was telling you guys about in Los Angeles, it was showing a transformer. And well, of course, it doesn't even look like a transformer, but the basic is the same. See? This was a ring, probably, I would say, 15 centimeter or something like that, but I didn't have to use ring, I used, straps. It's the same concept. So you can see 180 degrees is a different wire, is a little bit thicker, and 180 degrees is a different wire. So if I have a DC, and then I connect to 12 volts or whatever, immediately I get momentarily induction on this. But I won't be getting a lot because DC cannot cause any induction. So he was so genius, he came up with this idea that, he had this ring, half and half, and I have no idea how many turns were, but, overall we're just estimating it was induction anyway. And, the more coil you have here, the more induction you get, the more voltage you have here, the more, but, it shows the basics. It's okay. So what he did, let me turn this on, you can see it. So what he did, that was amazing. I have never seen in any book explain this. When you pull this coil inside the magnet, it's half of the AC. When you pull this out, it's another half. Nobody explained that. Nobody. Well, of course, he knew it was induction, but the poor man had no idea, unintentionally he had discovered the alternating current. So we didn't have to wait for Nikola 60 years, but he was genius anyway. So what he did on this, so he cut this on and off, on and off. That was exactly the same thing. I mean, his mind was so prepared, and that's amazing how he came up with this transformer. And in fact, this came up the basis for the transformer. And this is called primary, this is called secondary. It doesn't matter. So always, if there is no transformer, we won't be able to transfer any, electricity from Minnesota to Los Angeles, from LA to New York City. Is a step down and a step up. It all has to do with the transformers. And everything has to do with the induction. So I show you now, let me turn this on. So what he did, let me see if this is connected. I think it is connected, yes. No, it's not connected. Okay. So I have to connect these. So I'm using 12 volts, but I have no idea how, was it 18 volts he used? Was it 10 volts? I have no idea what he used, but the concept is the same. But see, now we realize his mind was so prepared. So every time you connect and disconnect this 12 volts. So what happened? Magnetic field is changing, polarity is changing. See, I show you. Let me see. Oh, it's not on yet. Oh, sorry, I didn't do it right. It should be here. I should be here, I'm sorry. I made a mistake there. Okay. So you see, this coil, 180 degrees, is connected to 12 volt DC, and this one is to multimeter. So did you see that? When I cut on and off, let me bring it closer, you can see. The induction almost less than one volt. And in fact, this came the basics for the transformer. I have so many other theories. I display one by one, and then I have to explain exactly what my theory is about. And then, unfortunately, I don't have a help today because I had a friend who would come over and film it. So every time I want to zoom, I have to get up. It's a little bit interruption. Sorry about that. Then I can start all over again. Okay, let me put this away, and then we can start the next experiment. But this is alternating. This is generator. And then I had to get this powerful magnet and then change everything inside. And in fact, this is a small, and I didn't want to deal with 120 volts because it's a little bit dangerous. But this one only gets 35, 36 or maximum 40 volt AC, which is safe. But my main concern was to show you that how the alternating current works. And in fact, today we are going to talk about alternating current, we are going to talk about magnetic braking, and we are going to talk about Lenz's law, which is the most important factor in induction. And induction is always followed by the Lenz's law. When I was doing my pendulum in university, I remember I told the student, never forget, always anything comes in a motion is followed by laws of thermodynamics. Now, laws of thermodynamics here is replaced with the Lenz's law. It doesn't matter what you do, anytime you have induction, there is an opposition. And that opposition is so good, but despite the fact we know that, every time we have an opposition, we have to do the induction. And this is the way I came up with this idea, because from 1920s I remember always I use for the angular momentum or anything like that, hand crank, see, because this is safe. I'm not going to get shocked or anything. I'm always avoiding 120 volts if I have to, but I'm expert anyway. It doesn't matter. But always I recommend you guys don't deal with 120 because it's a little bit dangerous and exotic. So, in order to show induction and the consequences for induction, I came up with these great ideas. So you may wonder why the AC always flickers. And then I realized this is the only way I can show you. I mean, if you read in a book, you won't be able to understand 100% why the AC flickers. DC, if you have a light bulbs, it never flickers. And the AC, like this, it doesn't matter. It can work with AC and DC, but electric motors won't work. So I show you. And then this part is so amazing. Let me do this one first. And when you see this experiment, how easy it is prepared, you will never forget what do we mean by Lenz's law. It's just easy. All you have to do, you have to experiment. See? Well, of course, this is 120 volts. And the frequency, I will explain it later. It doesn't matter. As long as the current goes in, it doesn't matter. AC or DC, it will work. Did you see that? It's flickering. But now I can go faster. See? This is the same. This is the same way. And then I show you exactly what do we mean by Lenz's law. So every time I have a load like this, well, of course this is not a big load anyway. This is like 40 watt. So every time we have a load like this, so it's not going to be easy to crank the handle. See, now I can feel the force. Oh gee, I did not connect it exactly the way I should have. Okay, it should be here. It should be here. It lights up a little bit. Did you see that? Now, if I connect two, that'll be harder. Now I have two like this. Let me see where they are. Okay, here. So these are two 120 volts, and then I did this on purpose so you can see what do we mean by Lenz's law. Because this is a big load compared to the other ones, and then I have to crank this harder otherwise to overcome that thing. If I won't be able to get any induction whatsoever. Okay, let me show you. Well, of course, I have to mention something. The reason why I chose this generator, because it's safe to work with. But if I connect this to drill 1500, I can light up anything. But I'm not going to do that because it's not safe. So all I have to do, see what happened here? I can hardly crank. I can hardly crank. Let me see if I can get light a little bit. I think I'm going to have to get up. Won't be able to crank it like that. Did you see that? Did you see? It's a little bit. But you can see it's always flickering because magnetic changing. Did you see that? It's a little bit glow. But this is the important part. This one, this time I came up with a unique idea. If I connect this to old meter like this one here, you can see the pointer is going back and forth and back and forth. Well, of course, I have to zoom it a little bit, you can see. So I set this multimeter to 50 volts DC. Let me show you exactly what happened. This is the only way you can visualize and conceptualize laws of physics. What do we mean by alternating current? See? Because the output is AC. Let me show you. Because the output is AC. So no matter what, this is going to go clockwise, counterclockwise, clockwise, counterclockwise. Well, of course, we did explain this before. Henrik Lorentz's here are in action. But did you see that? I have to bring it closer, you can see. So you see, it's going back and forth. So the faster I go, and then the deflections become smaller. The reason why, I'm getting more frequency. Let me show you. Did you see that? How fast that goes? So this is the only way you can see what do we mean by alternating current. So it's going up and then going down. It's a sine waves. And in fact, it's so versatile, so good, we would not even survive with anything like this. Okay, now I can go to next experiment. Before I start Michael Faraday's first electric motor, I have to explain it a little bit. You know, this is thick, but you can consider this wire. So every time you have a current, it's a concentric lines like this all around. In fact, I can replace this wire with earth. It's exactly the same inverse square law. So you further you go from this is getting weaker. But it's amazing. This is like a rotating wire. So if it goes in a magnetic field, what it can do, it can rotate. That's exactly like Michael Faraday did. But I don't know why the books don't mention that, why he was using a cylindrical magnet. He was not using bar magnet like this. That is amazing, because these are deflecting 360 degrees. But this, no, magnets are so amazing. It doesn't matter, even you throw it in air, they just rotate and then orient themselves. But there's no way you can do this because this is round. So what he did, Michael Faraday, was so genius. He had a jar like this. It was glass, I think. And at that time, there was no electrolyte or anything. But he was so genius, he had to use the only metal which is at the room temperature. It's conducting perfectly. But of course, at that time, they had no idea that the mercury was not safe, it's poisonous, and so and so. But he did it. But the only difference nowadays is if you don't use the mercury, you can use salt water or electrolyte. The protons conductor are inside. But what Michael Faraday did was electrons is the same thing. So he had a magnet here, and then he had something like this, copper, it was rotating like this, and then the circuit was completed. One was plus, and the other side was, plus, And then, he realized as long as the power is on, this mercury is making connection and it's going round and round and round. Well, of course, nobody knows exactly what's this like, 25 RPM or less, but it shows that interaction between magnetic field, moving charges and magnetic field. Well, Fleming was amazing. He called this right-hand rules. So what he did, he said, if you have something like this, so this is the force, and then your finger is a magnetic field, and this one is going to be current. So what he did, he put this, and then he realized that, these concentric lines are going counterclockwise, but the, wire itself is going clockwise. And then as long as there was a power here, it was going round and round and round. And unfortunately, I don't have everything here because this is a new lab. I moved in and then I just lost most of my equipment, and I have to buy most things, and then I'm hoping, I can get back to the way it was in Denver, Colorado. Okay, I can go to the next one now. This, I had to use neodymium because these are so powerful, and this shows exactly. Well, of course, this is not my experiment. His name was French scientist Dominguez Arago. Then what he did, he used like a pendulum. See, if I take this away, you see it's going to go back and forth, back and forth. Look, see. It has to move a little bit forward. Okay. See? But as soon as I put this, so what happened? The induction stopped us immediately. Look. Did you see that? Well, of course, this part is my idea. This is called Vahan's version. So either you use like a pendulum, this goes back and forth, or you slide this back and forth, it's going to be the same way. Did you see what happened? This is my idea. So induction happened. Well, of course, I have to explain exactly how this works. This is called magnetic braking, and it is used in industry, in theme parks, and it's so safe. Even if there is no power, they work because magnet does not require any power anyway. Did you see? And then I came up with another idea for the braking also. I'll show you. Well, the reason why I used this, not aluminum, because the permeability is so good. Okay. So I got two neodymium. They are like 3 millimeters apart. So you see, when I do this like this, it rotates about 4 seconds. But as soon as I put this in, see, it stopped immediately because it's so powerful. And it doesn't matter if I move this magnet or if I move the disc. It doesn't make any difference. You get the induction. And in fact, Michael Faraday once did this, and it was not successful. It's called monopolar. It had a huge disc, almost like 40 centimeters, I believe, across. And then he put that disc, and then at that time there was no neodymium. He used the ordinary. And then he was getting a little bit induction, but you know, he discontinued that anyway. So this is the basics for the magnetic braking. You see? You see how? It's impossible because its magnet is so safe and it will stop everything immediately. This is the one I have seen in most books, which is so good for a student. And let me see where I put it. So what I have here is cardboard. Well, it could have been plastic. I have like copper and I have aluminum. But this important fact over here is called permeability. Copper is the best. Aluminum is not. Even when it comes to, you know, electricity resistance, aluminum is 30% less. So when I drop this from, I did it like 60 degrees, see? 1 second. This one will take 3 seconds. Did you see? But I will explain why. And this one, copper takes 4 seconds. 5 seconds. Let me see what else do I have here. I discussed this like a month ago. So every time anything is suspended like this, it has a mass, it's going to go counterclockwise due to Earth differential things. But you know, this induction is so powerful as this goes counterclockwise, and then as soon as it enters in a magnetic field, it stops. Because that is so powerful. The induction is extremely powerful. Look, see? So I just go in a magnetic field, see? It stops. And the good thing is, it can rotate with the magnetic field, see? We do this one too. You know what? It doesn't make any difference. If I use the other one, the electric one is the same way. So see, they rotate now. Did you see that? They stop immediately. Because that is so powerful. That is the way that induction works. Now I'm going to have to zoom a little bit so I can explain exactly what I mean. Because there's so many things I have to explain. Let me see, what else do I have? I have one more and then I'll show you later. I have to zoom it so you guys can see what I mean by that. Okay. I'm going to zoom this a little bit. Okay, now I can explain. I got 4 pages, but I have to explain. So, induction motors can operate mechanically with DC by Vahan Davoudian, physics experimentalist. Email vahandavoudian@aol.com. And in fact, Michael Faraday did this in 1831. And you know what? When I was in LA in 1977, like I said, I found the old book, and then I realized there are some facts they are missing. And then one of them was the constant, and then I show you what I mean by that. That was completely missing, because nowadays, formula is so different. Let me show you. Okay. So this is the one I found, the book I was telling you guys, like 70, 75 years old, and it was in 1831, and this was the formula. CEMF, counter electromotive force, is equal to N, which is the number of loops, pi, the magnetic field, and divided by 10 to the power of 8T. This is so important. Nowadays, when I see the formula, that part is missing completely. That is a constant. This is the new one. E is equal to minus. Well, of course, this is a good idea. Means can go both ways, and N is the same way. And then they added this D, which doesn't make any difference anyway. Pi B dt. I mean, how could you eliminate a constant? This constant is so important. It says if 100 million flux lines are cut in 1 second, you get 1 volt. And that book, it was there. I took this note, and then I kept it all these years, and then I checked all the physics books. I have never seen this before. Think about that. Max Planck was amazing scientist. I mean, how could you tell E is equal to F? You can't. They say E is equal to H multiplied by F, the frequency. So this is a constant. H is a constant. You see how little this is. 6.6261 times 10 to the power of 34, minus 34 joules. I mean, there is no way you can ignore this. You have to add that thing. And then I remember, one time I discussed this with Scientists said, yeah, I don't believe in this 10 by 8. I said, yeah, that book was so old, and this is the way that constant is moving. How could you say speed of light is 186,000 or 300,000 kilometers? See, that is a universal constant, because the constant never changes. Like I said, the poor man had no idea that he had discovered the AC, and then nobody said anything about that, and then they said it's just the induction. No, that was induction. But when the coil goes in, it's one side, one part of the AC, and then comes out is the other side. That is the way it does work. Anyway, so let me see what else do I have here. And this is an amazing experiment I show you by end of my theory. In Westminster, I had wooden wheels like this. It was 100 teeth, but this is only 26. But I show you, it's only 26. So what I did, I had this on and off, and then I had to operate the induction motor. Well, of course, it was not real fast, but it was rotating. It was showing that, it is possible that you can use the DC and convert it to AC. Well, every time you cut on and off, what happened? The magnetic field is changing. So let me show you that. So this is the induction, and I got this from the oven, I think, yeah. So I have a battery here. So what it is, these gears are going on and off. Let me show you. Let me turn this on so you can see. Did you see that? It turns slowly, but it does. So the reason why this goes slow, because the frequency is not good. And the generator I show you guys, I could go like 1,500 RPM with my electric, with my drill, but I would not even get closer to 40 hertz. Because in order to operate this must be exactly 60 hertz. Well, of course, this is so small, it doesn't matter. Inductions are so different. If it's not 60, it's not going to work. And nowadays, there are so many induction motors. This is a little bit different. The reason why is a fan ceiling. So you can see it's exactly opposite. 99% of the time, the coil is the stator and the rotor is the induction. But this one is different. You can see, let me take this out. If I can. You see? So, in fact, this is getting rotated. This is the stator, but this is the stationary. But overall, you can see that makes a big difference. Well, of course, these are not really powerful. But always in an induction motor, there's a way. These are single phase. Well, of course, I'm not talking about 2 phase or 3 phases. So see those coils, primary and secondary or auxiliary? So these are exactly 90 degrees perpendicular compared to this. So causing torque and less and more. Well, of course, the ones in the bathroom is a little bit different. I show you. it's called shading, and then they have two wires, and that is causing delay. But I show you. We put this down. Let's see if I haven't missed anything. I hope not. I think I've covered everything. Yes. And this is another induction. You can see stator is not there. But see, induction is so different. So you got the ferromagnetic and paramagnetic all together. But you see those lines? It's not. It's torquing. You know it. And this is the one I removed from a small induction. I'll show you. You see, even if it's outside the thing, see, it's rotating. Let me see. See, this is the actual rotor, but you can see this is ferromagnetic. And did you see that? Well, of course, I don't want to go in because it's going to be so fast. It's going to be magnetized. So let's see, what else do I have here? And this is a zinc. This will also rotate inside. Well, it's not going to be good anyway, powerful anyway. This is another one. Did you see? It rotates real good. Let's see what else do I have. Now I have to take care of my posters. So it's amazing. Lenz's law is so important. Every time we have induction, is followed by Lenz's law. I remember at Christ's University, I was, having a speech. And then I told the student, every time you have laws of motion, like pendulum or anything, it's automatically followed by laws of thermodynamics. There is no way, even in subatomic size, even you have that. And then this is exactly what happened. Every time you have induction, Lenz's law is already there. I show you guys, when you have more load, it's not easy to turn because it's just opposing. So this was the wheel I show you, and then like I said, this is going cut on and off and off. And then what happened, this is every time it's changing magnetic field, and the induction is so powerful. Every time you bring something inside, well, it shouldn't be iron, it should be aluminum, copper, it will stop immediately. And these are the sine waves for the AC, and like I said, it goes up and then goes to zero and then comes back. But amazing thing about the AC, it does the work, but the DC cannot do that. But unfortunately, the origins of most scientific discoveries and inventions are shrouded in a history of haste. Sometimes they did not write exactly what happened. Okay, this is another poster. I mentioned this a few minutes ago. So imagine this is the magnet, and then you can see this is going arrows down and this is going down. So as the magnet moves, it's changing polarity. That is amazing. And like I said, copper has the most permeability. Permeability means how good they can handle the flux lines. Aluminum is less, and then like iron is amazing. Iron is 7 times more. Copper is 1.25, and then the other one is 1.25, but ferromagnetic are 7 times more, so that's why they use it. So, and this is the one I showed you before. These are 2 magnets, so it doesn't matter anything rotating as long as it's not ferromagnetic. It goes inside, and then the induction is so powerful it stops it immediately. And this is the one I show you guys for the French scientist he did. This is like a pendulum, but this one is my version. Because laws of physics are so amazing. Reversibility of laws of physics is so good, and Lord Kelvin was one of the greatest in these ideas. Laws of thermodynamics are reversible. So is this one. Imagine, see, he did it this way, I did it the other way. It doesn't matter. As long as you have a motion, it's going to work. So if you have this electric motor, you turn it mechanically, you're going to get electrical energy. And the other way, you get electrical energy, you get mechanical. So it's reversible, that is so good. And this is what happened, and this was the formula I told you guys that, unfortunately, this 10 to the power of 8 is missing. And then if you ask someone how many lines are cut to get 1 volt, and I tried to do this many years ago, and then I realized it's more than the speed of light. They are traveling so fast. I mean, it's amazing, the flux lines, how good they are. And so I have one more poster, I think, and that is going to be it. draw this so you can see exactly what happened. See? How the AC is getting generated. See? Look at there. So you got 90 degrees, you get half of that sine wave. You get 180 degrees, it's exactly one complete. See? And then we get 270, you got 1.25, and you got 360, it's going exactly 1. So if there is another one here, from here to here is the wavelength. So imagine alternating current is so amazing. It changed our life. I mean, how could you expect to do, step-up transformer, step-down transformer, and, from, Los Angeles to New York City and back and forth? How could you do that? If you don't have a transformer, if you don't have induction, there is no way. Always you do have like a step-down transformer and then a step-up transformer. And by the time you get to the houses, you have a step-down. And that is the way we save money. That is the way we survive. With the DC, we cannot survive. I remember when a long time ago, Nicola was there, and then there was always a controversy that AC is exotic, is bad, but it was misconception. AC is the life. So anyway, this is another thing. And now let's see what else do I have here. And imagine, parks and recreation places like Magic Mountain in Los Angeles, and imagine all those people are using magnetic braking. Because there is no way, I mean, it's so safe. Magnetic braking can stop like hundreds of tons. There is no way you can stop it with your, friction, because it's going to catch fire. But, magnetic braking is so safe, is so good. And imagine, I remember, it goes 104 miles or 168 kilometers in 7 seconds in Magic Mountain. I mean, how could you do that? It's all because of induction. Imagine, you have the button like this, and then you unroll it, and it's going to be synchronous, linear induction. So what happened, that is the way they used always. And then next week, hopefully, I will have the magnets. That is going to be so exciting, because these are special things that's never been revealed. And in fact, I just wanted to thank everyone for your support and your encouragement, and I love it, and thanks a lot. And then I do my best to get more theories for you guys next week about the magnets, and then we have like 6 more theories. Every week I will publish one, and then like I said, the most important thing for me is the feedback, because in science, if there is no feedback, there is no oscillation. Even the atomic level and the subatomic level, there must be feedback, otherwise there won't be any oscillation. If there is no feedback, nobody knows how good you did it. So your ideas, and they honor your ideas, and then I like to even meet you. You have my email, you have my everything. You can email me, you can even send your things to me, and then I would appreciate that. And thanks a lot anyway for spending time with me. Thank you.